Okay, Assalamualaikum warahmatullahi wabarakatuh. So for today, we will continue our lesson in the same topic 6.1, that is radioactive decay. So before this, we have learned for a radioactive element, the nucleus is unstable. So what happened? It will emits the radioactive emission to become more stable nucleus. So we have three types of radioactive emissions, that are alpha particle, beta particle, and also gamma ray. When unstable nucleus emit the radioactive emission, it cannot emit alpha and beta at the same time. It only can emit alpha particle or beta particle. But for gamma ray, it can emit gamma ray, and it can emit gamma ray with alpha particle, or it can emit gamma ray with beta particle. But it cannot emit alpha and beta particle at the same time. Okay, so why it can emit gamma ray with alpha particle, it can emit gamma ray with beta particle? So the gamma ray is an electromagnetic wave. So it didn't affect the nucleon number and the proton number of the elements. So means that the nucleon number and the proton number of the element is unchanged. Means it will become the same element. The effect of gamma ray, it will affect the energy level of the element, where the energy level of the element will be decreases. So means that the nucleus, after the radioactive emission, the energy level will be decreased. So when it emit alpha and beta particles, so the nucleus, the element will be changed, because alpha and beta has a nucleus, where alpha is a nucleus of helium 4-2, and beta is an electron E0 negative 1. Okay, that's what we have learned. We have three radioactive emission, three types of radioactive emission: alpha, beta, and gamma. And also we have three types of radioactive decay, that are alpha decay, beta decay, and gamma decay. Okay, so that's what we have learned. So for today, we continue with half-life. For a radioactive element, when it emits the radioactive emission, it has a half-life. So what is half-life? Okay, when a sample radioactive material decays, what happens? The number of parent nuclei which has not decayed will be decreases, and the number of daughter nuclei will be increases. The daughter nuclei is the new element produced from the radioactive decay. That is what we call as daughter nuclei. The parent nuclei is the element before the radioactive decay. So the parent nuclei that has not been decayed will be decreases with the time, while the daughter nuclei will be increases with the time. So what is half-life? Half-life is the time taken. When we say life, means that we want to measure a time. The time taken for a sample of radioactive nuclei to decay to half of its initial number. So that is half-life. And for half-life, the symbol we use T half. So the T half is the symbol that we use for half-life. And that's the meaning is the time taken. You want to measure the time taken for a sample of radioactive nuclei where the nucleus is unstable to decay to half of its initial number. So we go for a concept of half-life later. After one half-life, the number of nuclei that are not decayed will be half. Okay, after one half-life, the number of nuclei that are not decayed will be half. of its initial value. When an unstable radioactive nucleus decays, the new nucleus that is formed may also be unstable. For a radioactive element, when it emits the radioactive emission, it cannot become a stable nucleus. It will become a more stable nucleus. Means that the process to become a stable nucleus, it has a series of radioactive decays to become a stable nucleus. When an unstable radioactive nucleus decays, the new nucleus that is formed may also be unstable. The new nucleus will experience a series of continuous decays until a stable nucleus is formed. Figure 6.5 shows a complete decay series of uranium-238 to lead. Lead also been known as plumbum. Lead-206 or plumbum-206 and their respective half-life. Okay, so we look for the uranium-238 decay series. Initially, we have uranium-238-92, an element be known by its proton number. When its proton number is 92, the element be known as uranium. So from the series, we can see that we have two uranium. One is uranium-238 and second is uranium-234, but the proton number is the same, that is 92. So the element be known as uranium because the proton number is the same, 92. Yeah. The nucleon number 238, the nucleon number 234 is different. So when the nucleon number is different, while the proton number is the same, the element be known as isotope. For the uranium-238, it emits alpha particle. Uranium-238 emits alpha particle, and uranium-234 also emit alpha particles. So when uranium-238 emits a radioactive emission that is alpha particle, it is a radioactive element, and at the same time it is an isotope. So uranium-238 and uranium-234 be known as a radioisotope because it is a radioactive element that have the same proton number but different nucleon number, that we call as isotope. Okay, that is radioisotope. Either than uranium-238, also a radioisotope is PO. PO here refer to a polonium. Polonium-218. We also have a polonium-214. So why we call it is a polonium? Because the proton number is the same, that is 84. And also we have another one, polonium-210. The proton number is 84. Okay. So when the proton number is the same, means that it is same element, but it has a different nucleon number that we call as an isotope. So polonium-218, we call it polonium-218 because it has 3 different nucleon number. So to know which polonium, we said what is the nucleon number of the polonium. Polonium-218, polonium-214, polonium-210 is a radioisotope. So there are 3 polonium because the proton number is the same, that is 84, but we call it as a polonium-218, polonium-214, polonium-210 because the nucleon number is different. So that's why we call it as polonium-218, polonium-214 and polonium-210. Okay, that is a radioisotope. Okay, we go back for uranium-238-92. Uranium-238-92 is unstable nucleus. It's a radioactive element where the nucleus is unstable. So to become more stable, it emits alpha particles. What is alpha particle? Alpha particle is the nucleus of helium. So when uranium-238-92 emits alpha particle, what happened? The nucleon number will be decreasing by 4. The nucleon number will be decreasing by 4. 238 minus 4, we get 234. And the proton number will be decreasing by 2. 92 minus 2, we get 90. So from uranium-238-92, it becomes a new element 23490, that is TH, where TH we call as thorium. So now it becomes a new element. So the half-life of the uranium-238-92 is 4.5 times 10 to the power of 9 years. A very longer time, longer periods. Okay. For the thorium-234, it is also unstable nucleus. So it is also emit the radioactive emission, but for the thorium-234, it emits beta particles. So what is beta particle? Beta particle is an electron with high kinetic energy or high moving electron. So when the thorium emit the beta particle didn't affect the nuclear number. The nuclear number of thorium is still the same when it emits the beta particle. So the nuclear number of thorium is 234. The new nuclear number is still 234. Unchanged. The nuclear number is unchanged. But the beta will affect the proton number, where the proton number of the thorium-90 will be increasing by 1. We have to plus 1. 90 plus 1. So the new proton number will become 91. So the nucleus changes to a new nucleus, that is Pa. 23491. 91 is Pa. What is Pa? Pa here is protactinium. Okay. So from thorium-234-90 to becomes 234-91 protactinium Pa, the half-life of thorium-234 is 24.1 days. Means that every 24.1 days, the number of atom thorium will become half from its original number. And the process will be continue until the process of the decay series produce a stable nucleus. So the stable nucleus here is 206-82. What is 82? 82 here refer to a plumbum or lead. So we call as lead 206. 206-82 Pb is a stable nucleus. When it reach a stable nucleus, the process of radioactive emission will be stopped. But it takes a very longer time to become a stable nucleus. This is what we call as a decay series of a radioactive element. Okay. From the diagram also, we can see that the gamma ray will be emitted with another particles. From plumbum 214-82, plumbum or lead 214-82 is a radioisotope, because the lead 214 is not stable nucleus, but the lead 206 is a stable nucleus. So the lead 206 is an isotope, but the lead 214 is a radioisotope, because it is isotope and at the same time it is a radioactive element. But for the lead 206, it is not a radioactive element because it is a stable nucleus, but it is an isotope. So for the lead 206, we call it as isotope. For the lead 214, we call it as radioisotope. Okay, from the lead 214-82 to becomes 214-83 Bi. Bi here is a bismuth. It emits a gamma ray, and at the same time also it emits a beta particle. So the gamma ray will be emit with another particles, maybe alpha, maybe beta. So why? Because alpha and beta will affect the nucleus, but the gamma didn't affect the nucleus. The gamma only affect the energy level of the nucleus, where the energy level of the nucleus decreases. The energy level of bismuth is lower than the energy level of lead-214. That is the effect of the gamma ray. And also from the bismuth-214-83 to become 214-82. Okay, so 214-83Bi bismuth to become 214-83. The nucleon number is still the same, but the proton number increasing 1 means that the bismuth emit the beta particle, and also at the same time it emit the gamma ray. So the gamma ray will affect the energy level of the bismuth, where the energy level of the bismuth is higher than the polonium-214. That is the effect of gamma ray. It will emit together with another particles, maybe alpha, maybe beta. This is the examples of the decay series for a uranium-92, 238-92 to become a stable nucleus lead-206-82. Okay, so we want to continue with half-life. What is half-life? Half-life is the time taken. So means that when we said life means we want to measure time. Time taken of what? Time taken for unstable nuclei to become half of its mass, or number of atoms, or activity from its original or initial value. That we call as half-life. Okay, half-life is the time taken for unstable nuclei to become half of its, either the mass, either the number of atom, or either the activity. Activity is the rate of emissions, the number of radioactive emission per unit time. That is activity from its initial or original value. That we call as half-life. The time taken, how long it takes for the unstable nucleus emits the radioactive emission, and the mass or the number of atoms or the activity to become half of its original value. So the half-life, we can label the half-life by using the symbol of T half. This is the symbol for half-life. Okay, we go for the concept of half-life. The half-life, to understand the concept of half-life, we can use the mass, we can use the number of atoms, and also we can use the activity. Activity is the rate of radioactive emission, the number of emission per unit time. Let's say initially we have 100 gram. So now we consider as mass. We also can consider the number of atoms, 100 atoms. We also can consider the activity, 100 per second. So that is activity. So let's say we consider the mass of atom. So initially we have 100 gram of mass. So the half-life is how long it takes for the mass of the nuclei to become half. Half of 100 gram is 50 gram. Half of 100 gram is 50 gram. So how long it takes from 100 grams to become 50 gram? So the time taken be known as half-life. So this is half-life, when we can measure the time taken. And the process is continuing. From 50 gram, how long it takes to become half of 50 gram? Half of 50 gram is 25 gram. So, how long it takes? The time taken also been known as half-life. So we continue from 25 gram to become half, that is 12.5 gram. How long it takes? The time taken been known as half-life. We can use the symbol of T half. And from 12.5 gram, how long it takes to become half of 12.5? That is 6.25 gram. So the time taken, if we can measure the time taken be known as half-life. Okay. For the same element, the half-life is the same. Means that the half-life from 100 gram to 50 gram is the same to the half-life from 50 gram to 25 gram. It's the same as the half-life from 25 gram to 12.5 gram. Is the same as the half-life from 12.5 gram to 6.25 gram. For the same element, the half-life is the same. Okay. So the concept of half-life also we can use a percentage in the concept of percentage, that when we say the percentage, initially we start with 100%. So what is the time taken for the radioactive element to become half of 100%? Half of 100% is 50%. So the time taken from 100% to become 50% is the half-life. From 50% to become 25% is half-life. From 25% to become 12.5%, the time taken is half-life. So the concept is still the same. Only we change the method from mass, change to a percentage. Okay. Another concept that we have to understand is the number or the mass of undecayed nuclei to the mass of decayed nuclei. Okay, it is inverse. So let's say initially we have undecayed nuclei is 100 gram. Initially we have undecayed nuclei is 100 gram. So when we start with 100 gram initially, means that at that particular time we didn't have a decay process. The decay nuclei is 0 gram. It didn't start yet for the decay process. So the decay nuclei is 0. So when the decay process start, so from 100 gram to become 50 gram, that is what we call as half-life. So means that when half-life, the undecayed nuclei will become half of its original mass. From 100 gram become 50 gram is undecayed. So where is another 50 gram? The 50 gram has been decayed. The 50 gram has been decayed. From 50 gram, for the same half-life, it will becomes 25 gram. Means that the undecayed nuclei will be decreasing half for every half-life, and the decayed nuclei will be increasing half. The decayed nuclei becomes 75 gram. Okay. So for another half-life, from 25 gram it will becomes 12.5 gram. So this is undecayed nuclei, the mass of undecayed nuclei. So what is the decayed nuclei? The decayed nuclei is 87.5 gram. So how to get 87.5 gram? So 87.5 gram is the subtract between the original, the initial mass of the element, that is 100 gram, subtract to the undecayed mass of the nuclei, that is 12.5 gram. So we get 87.5 gram. Means that at each time of decay, the mass, the number of atoms, the activity of the element must be constant. If we have 100 gram, always each half-life we must have the total mass must be 100 gram. Okay, the total mass must be 100 gram. But the difference is the undecayed mass of nuclei will be decreasing, while the decayed nuclei or the decayed mass of the nuclei will be increasing. Okay, that is the concept of the half-life. Okay, the concept of half-life can also be expressed in the form of a decay series as follow. We can use a mathematic method. So initially, let's say we have N0. N0 we call as N0. 0 is not. N0. N0 or NO is the original value. N refer to the number of atoms. Actually, N refer to the number of atoms. So half-life means the number of atoms will become half from its original value, N0 over 2. So when it goes for the second half-life, the number of atoms will be half of half original value. So we get 1 over 4 N0. When we go for the third half-life, the number of atom now is 1 over 2 to the power of 3. Means that 3 half-life, 1 over 2 times 1 over 2 times 1 over 2 from the original number of the atoms. So we get 1 over 8 of original number of atoms. So, and 0 over 8. And the process will be continued until it becomes a stable nucleus. So we can write the equation as a simple. We can write the equation: the number of radioactive nuclei that has not decayed. How to calculate? We use the equation of n equals to half to the power of n times n0. So what is n0? N0 is the initial number of radioactive nuclei. What is capital N? Capital N is the number of half-life, and the number of life must be an integer number, is a positive integer number. It cannot be the decimal number. And T half is the half-life of the radioactive emission. So to know the number of radioactive nuclei, we can use the equation of N equals to half to the power of N times N0, the initial value, the initial number of the nuclei. The equation also can be used if we want to get the mass of radioactive nuclei. So the mass, the equation will change to half to the power of n times the original mass. Or also we can change to A. A here refer to the activity, the rate of emission is half to the power of n times the original activity. So the concept of half-life, we can use the mass of the nuclei, the activity of the nuclei, we can use the number of atoms of the nuclei. That the half-life is the time taken for the mass, for the activity, for the number of atoms to become half of its original value or initial value. In the form of diagrams, so we can use this diagram to understand the concept of half-life. Half-life, we start with initial condition where the number of radioactive nuclei has not decayed. We start with N0. So while the number of decayed radioactive is 0 lah, because the process didn't start yet. So N0 minus N0, we get 0. For the first half-life, this is the first half-life. So the number of radioactive nuclei has decayed will become half of its initial values, and the number of decayed radioactive nuclei will be half, because N0 minus half that has not decayed, so the number of decayed radioactive will be half of its original or initial number. For the second half-life, this is second half-life, T half. So the number of radioactive nuclei has been decayed is half to the power of 2, because the second half-life times the initial number of nuclei, N0. So we get 1 over 4 N0. And the number of decayed radioactive has been decayed is N0 minus to the 1 over 4 N0. We get 3 over 4. 3/4 has been decayed, 1/4 not yet decayed. For the third half-life, T half-life, this is the third half-life, the number of radioactive nuclei has not decayed is 1 over 2 to the power of 3 to the initial number of nuclei. So we get 1 over 8. And the number of decayed nuclei has been decayed is N0 minus to 1 over 8, that we get 7 over 8 N0. Okay, and the process is continued to the fourth, to the fifth, to the sixth half-life process. Okay, so what we can see from the diagram of atom here is the red one is the radioactive nuclei that has not decayed, while the white is the decayed radioactive nuclei. So initially, all the nuclei, all the atom has not decayed. After one half-life, half of the atom has been decayed and half not yet decayed. For the second half-life, so we get a quarter of nuclei has not decayed, but 3/4 has been decayed. Okay, and the process is continued. This is the concept of the concept of half-life in the form of diagram. So in the form of mathematics equations. So that is half-life. So the concept of half-life also we can use in the form of graph. We can plot or we can draw a graph. So when we set graph, we must have two axes. So our vertical axis can be mass. Our vertical axis can be number of atom. Our vertical axis can be activity of the nuclei against, but our x-axis is time, because we want to find the time taken for the mass, for the number of atom, for the activity of the nuclei of the radioactive element to become half of its initial value. So when we plot a graph, we have two axes. We have two axes, vertical axis and horizontal axis. So the vertical axis can be mass, number of atom and activity. Let's say we use number of atom. So number we didn't have any unit, but if we use mass, we have unit gram or kilogram. While the x-axis here refer to the time. The time may be in the unit of second, maybe in the unit of minute, maybe in the unit of hours, a day, a week, a month, a years. So let's say we use the unit of second. Okay, how are we going to determine the half-life of the radioactive element from the graph? So first we have to know what is the initial number of atoms. So let's say the initial number of atoms start here. This is N0. So we use the symbol of N. So the half-life is the time taken for the element, for the nuclei to become half of its initial value. So N0, half of N0 is here. This is half of N0. Okay. And what is the time taken is the half-life. So the graph of the radioactive decay, is an exponential graph. It's like an inversely proportional graph, but it is not an inversely proportional graph. It is an exponential graph. This is exponential graph. If you learn at maths, maybe you learn this form of graph, exponential graph, like a graph that has a relationship of inversely proportional. Okay, to determine the half-life of the nuclei, we have to draw a line when the number of atom is half from the initial value. So half, we draw a horizontal dotted line until it touch the graph of the radioactive element, and then we draw a dotted vertical graph until it intercept with the time axis. So what is the value when it intercept at the time axis is our half-life. That's how we determine the half-life of radioactive element from the graph. Okay, if we didn't get the exact value of half-life from our graph, so we can do a next half-life. So the next half-life is half of half N0, that is 1/4 N0. Same as what we do for the half-life. We draw a dotted horizontal line until it touch the radioactive element graph. and then we draw a vertical dotted line until it intersect with the time axis. Okay. Okay. So what is the value that we get from the intercept? This is our 2 half-life. 2 half-life. So to get the half-life, we have to divide by 2. Okay. So same as when we draw the next half-life, that is 1/8 of n0. That is our third half-life. What is the value that we get? So to get the half-life, we have to divide by 3. Okay. So from here, we can see that the curve graph of radioactive decay is as shown in figure 6.7a. So this is the graph for a radioactive decay, where we call as exponential graph. The shorter the half-life of radioactive sample, the higher the rate of decay as shown in diagram 6.7b. Okay, from the diagram 6.7b, the red graph has a shorter half-life compared to the green graph. The green graph has a longer half-life. So the shorter the half-life, the higher the rate of the decay process. The longer the half-life, the lower the decay rate of the half-life. That is the meaning of the shorter the half-life, the higher the rate, the longer the half-life, the lower the rate of the decay process. Okay. So we go for an example. Half-life is the time required for a mass or activity or the number of nuclei of a radioactive substance to fall to half of its initial value. Determine the half-life from a decay curve. So the y-axis, the vertical axis is activity, is the unit is the count per second, and the x-axis is the time in the unit of hours. So to determine the half-life, we have to know what is the initial values of the nuclei. The initial value is 256. So half of 256 is 1 to 8. 1 to 8 is the half of 256. 256 divide by 2, we get 1 to 8. So it is half activities from its initial activities. So what is the time taken? So the time taken we get from the graph is 3. 3 what? 3 hours. So the 3 hours be known as half-life of the elements. So that's how we determine the half-life from the graph. Okay. We go for another example. So this is the example what we have discussed. The original activity is 256. Half of 256 is 1 to 8. So what is the time taken for the element, for the activity of the element to become half of its initial activity? 256, half is 1 to 8. It takes 3 hours. 3 hours be known as half-life. Solving problem involving half-life. A sample of radioactive material stored in the laboratory has an initial activity of, so the initial activity is 480 per second. The half-life 6 minutes. Okay. How much its activity after 30 minutes? Okay. So how to solve the problem? First, we have to identify the problem. The problem is we want to know the activity of the element after 30 minutes. That is the problem. Second step, we have to identify the information given from the question. From the question, it gives an information, the initial activity 480, and the half-life is 6 minutes. So we go for the third step, is identify what is the formula that we're going to use to solve the problem. So to get the final activity, we have to use the equation of mathematics. A equals to half to the power of n times the initial activity. So what is the number of half-life for 30 minutes? So 30 minutes. The half-life is 6 minutes. So 30 minutes divided by 6 minutes, we get 5 half-life. So use the equation A equals to half to the power of n, where n is 5 times the initial activity is 480. So we get 15 and the unit is per second. Counts per second. So that is example 1. So for example 2, a radioactive material stored in the laboratory has a half-life of 10 days. Calculate the number. We want to find the number of days taken. Calculate the number of days taken for the activity sample to reduce 25% of its initial activity. So this information in the form of percentage. So we start with 100%. Half of 100%, it becomes 50%. That is our first half-life. From 50%, half becomes 25%. That is the second half-life. So from 100% to 25%, it takes 2 half-life. Where 1 half-life is 10 days. So 2 half-life, we have to times 2 times 10, we get 20 days. That is the time taken for the activity to become 25, to reduce 25% from its initial activity. Okay, this is another example. The time taken for the number of undecayed. So to know the undecayed nuclei in the sample to be reduced to half of its number, original number, we can use the equation of n equals to half to the power of n, where n is the number of half-life times the initial number of atoms. Okay. Let's say in 30 days, the activity of a sample of radioisotope decreases to 1/8. 1/8, it means 1/8 of its original activity. Calculate its half-life. Okay, our equation is half to the power of n times n0. This is n0. So 1/8 of n0. 1/8. 1/8 is 2 to the power of 3. This is 1/8. 8 is 2 to the power of 3. 2 to the power of 3 is equals to 8. So the number of half-life is n. So what is n? N is equals to 3. So this is the number of half-life. Okay. So means that we have 3 half-life. So 1 half-life, 30 days, it takes 3 half-life. So what is the half-life? 30 days, 3 half-life. So 1 half-life we have to divide by 3. So the half-life is 10 days. Okay. So this is another example. PA is a protactinium, takes 2.8 hours to shrink from 80 gram to 5 gram. How many half-life are there? So we can solve the problem also by using a diagram. 80 gram half is 40 gram, 40 gram half is 20 gram, 20 gram half is 10 gram, 10 gram half is 5 gram. Finally, we get 5 gram. So from 80 gram to 5 gram, how many half-life do we have? 1, 2, 3. We have 4 half-life from 80 gram to become 50 gram. So we have 4 half-life. Another example, the radioactive atom in a substance decay to become stable atoms. It was found that after 288 seconds, 6.25% of the atom have not decayed. What is the half-life? What is the half-life of the substance? So originally, when we use the percentage, we start with 100%. We want reduce to 6.25%. So 100% half is 50%. 50% half is 25%. 25% half is 12.5%. And 12.5% half is 6.25%. So we get finally 6.25%. 6.25%. Okay. How many half-life do we have? 1 half-life, 2 half-life, 3 half-life, 4 half-life. We have 4 half-life. Okay. 4 half-life, it takes 288 seconds. So what is the half-life? So we have to divide by 4. So the half-life is 72 seconds. So that how we calculate the half-life of the element. Okay. Another question, the half-life of iodine-131 is 8 days. So the information given is the half-life of iodine-131. A radioactive sample contains 64 grams of iodine-131. Determine the mass of iodine has decayed and has not yet decayed after 24 days. So the half-life is 8 days. Okay. For 24 days, how many half-life do we have? 24 divided by 8, we get 3 half-life. So 3 half-life, what is the mass for the element that has been decayed, and what is the mass has not decayed? 64 half is 32 gram. 32 gram half is 60 gram. 60 gram half is 8 gram. So how many half-life? 1, 2, 3 half-life. So when for the 3 half-life, the mass of iodine has not decayed. Not decayed is 8 gram, while the mass of iodine has been decayed is the initial mass. So the initial mass is 64 gram. Subtract to the mass that has not decayed 8. So the mass has been decayed is 56 gram. Okay. Another example. A sample of lead 211 of mass 96 gram, half-life 36.1 minutes. What fraction? So this question want to get the answer in the form of fraction, we have to give a fraction. Okay. What fraction of a sample has not decayed after 108.3 minutes? Okay, the half-life given is 36.1 minutes. That is the half-life given. So after 108.3 minutes, how many half-life do we have? 108.3 divided by 36.1, we get 3 half-life. So we have 3 half-life in 108.3 minutes. So start with initial mass, that is 60 gram. For the first half-life, it becomes 48 gram. For the second half-life, it becomes 24 gram. For the third half-life, it becomes 12 gram. 12 gram is the mass of undecayed, that has not decayed. That is 12 gram. So 12 gram in the form of fraction is 1/8. What fraction of the sample has not decayed after 108.3 minutes? So the mass is 12 gram. The fraction is 1/8 because 1/2 to the power of 3. 3 is the number of half-life. So 1 half to the power of 3, we get 1/8. Okay. So what is the mass of the decayed products after this period? The decayed product has been decayed is initial mass 96 minus the mass that has not been decayed is 12, that we get 84 gram. That is the mass that has not been decayed. Okay, another question in the form of a graph. Sketch activity against time graph to show the decay of a radioactive substance. Explain how the half-life is determined. So when we want to explain by using a graph, first graph must have an axis. So axis, we have 2 axes, vertical and horizontal. So our vertical axis refer to the activity or mass or number of atom, but our horizontal axis refer to the time. Okay. Second, we have to draw the form of the graph. The form of the graph is an exponential graph. Start with the initial activity, that is n0. So we have to label n0 and draw the exponential graph. After that, we have to label the half of n0 and draw a dotted line horizontally, touch to our exponential graph, and then draw a dotted line vertically and intercept with the time axis. And the value intercept at the time axis is our half-life. Okay, that is half-life. That's what we have to understand with the half-life. So Next, you can do the exercise to make sure that you can understand what we have learned in the concept of half-life. Okay, in the exercise, already given the answer. The red one is the answer, at the right side is the answer. If you didn't get the answer, please ask in the slot of physics, in the class slot of physics. Please ask which question that you can't answer, you can't understand. Please ask your teacher. That's for today. Assalamualaikum warahmatullahi